Hi, it's week 4, and again, what I'm doing this week is using a video from last year. Um, Looking through it, I want to talk before I do each of these videos or before I reuse them. Just have a little discussion about what not to pay attention to. If there's any reference to a specific date or that something is coming up or something's due in the video. That was last year, and it does not apply to this year. So I'm reusing the videos because I think they came out pretty well, and I don't see any point in reinventing the wheel. But like I say, the downside is there may be some references to stuff from 2020 in there that do not apply to 2021. So again, just to remind you, if we're going to have a test or if we're going to meet in person, that's going to come by email. You'll receive an email telling you what's going on. So if there's any reference to that in this upcoming video, just ignore that. As always, if you have questions about the content, if there's something you don't understand, then please email me, call me. You'll leave a message, but I'll call you back and we can talk about it. If we have to, we can do a web meeting, a WebEx or something like that, Zoom, whatever. So you can talk to me face to face about it, even if we can't arrange for a time to meet in person. So I'm here to help, get you through this and try to make sure you understand everything. And so if that's what we have to do, that's what we have to do. So just watch this video. This, of course, is 2021, and I'm telling you, there is a test coming pretty soon, but I'll be announcing that by email. Once again, everything will be by email. Hello again, fourth lecture now, fourth week, really third full lecture for engine performance AU-264, and we're going to continue where we left off the last time, and I always like to kind of remind you where we left off. So what we were doing, let me bring this up for you, right? Under engine performance here, let me get rid of the video of me. Under engine performance, any one of these, whichever one shows up on your screen, AU-264, we have lessons, same place we've gone every time. These are the videos I've already posted, first, second, and third. Obviously, you're watching the fourth, so it will be up here. And we're still under Module 1. And under Module 1 slides, if we open that up, and you can do this yourself or just follow along with me here. We were on the one, we'd gone through all 4 strokes, and we were about ready to start talking about engine air fuel requirements. So that's where we're going to pick it up now. And let me get this full screen here for you. And we'll start talking about it. So I have a bunch of bullet points here. Let me talk about each one of them. So in the internal combustion engine, which is, the gasoline engines we're talking about, or diesel, what happens is there's an air-fuel mixture put into the cylinder and then ignited. And burning is, another word for burning is oxidation. In other words, it takes the fuel and combines it with oxygen. And in doing so, a lot of heat energy is released. So we need both fuel and oxygen in order for the combustion process to happen. Anybody that's ever covered a candle or anything like that knows that the flame goes out pretty quickly once you take away the oxygen. And if you take away the fuel, obviously, same thing happens. So you need both. Where does the oxygen come from? Comes from air that's mixed with the fuel either during the intake stroke. So let's talk about that a minute. For the first probably 80, 85 years that cars have been around, a carburetor was used. And a carburetor was a simple mechanical device that as air flowed through it, flew through a restriction that created a little bit of a low pressure area, and then that caused fuel to be drawn in, and what controlled the quantity were little jets, little metered orifices that the fuel would flow through. Then we moved in the mid 80s to something called central fuel injection or throttle body injection, where one, maybe two injectors were placed outside of the intake manifold, above the throttle plate, not inside the engine itself. And those injectors supplied fuel to all 4, 6, or 8 cylinders, just 1 or 2 injectors. And then sometime in the 80s, it became more and more common for port fuel injection. So port fuel injection means the fuel injector was located right in the intake port of the engine. So as the air flows in the intake valve, just as it's passing, near that valve, fuel is sprayed from the injector into that incoming air stream, and it's sprayed in atomized. In other words, in a fine mist, and so then it evaporates. And only, this is really important, only fuel vapor burns. Liquid fuel does not burn. I'll come back to that in a second. So more recently, on a lot of engines, air is drawn into the cylinder without any fuel, and then fuel is injected directly into the cylinder, and they call that direct injection. So there are a lot of advantages as time went on. Carburetors were not very precise. They worked pretty well. I mean, you had engines that made a lot of power and all that, but as far as emission controls and fuel economy, not so good. And then throttle body injection was kind of, how can I say this? In the computer world, they call it a kludge. It's where you take some technology and kind of put it together with baling wire and duct tape and make it work, but it's not really a good solution. Throttle body injection was, you had the Clean Air Act, you had corporate average fuel economy standards that manufacturers were not able to meet with carburetors, but they didn't really have decent fuel injection systems ready to go, so they unbolted the carburetors and put these throttle body injection units right where the carburetors used to be, and they were able to more precisely control the air-fuel mixture, but still a lot of the problems with carburetors were with throttle body injection. You're injecting the fuel so far away from the cylinder that cylinders closer to the injector unit would get a richer air-fuel mixture. Cylinders farther away would get a leaner air-fuel mixture, so the power output of the engine wasn't even. Cold engine, maybe that fuel would condense on the intake manifold runners between the throttle body and the actual intake valve. Just all kinds of problems. They didn't run well. I was in the dealer for all that. When I started in the dealer, it was the mid 80s, early 80s, and most of the vehicles were throttle body injection at the time, and they had all kinds of they just didn't run well. Let's put it that way. When port fuel injection came around, that was a lot better. And there were two kinds of port fuel injection systems. One was called bank fired, so bank, B-A-N-K. And so think of a V-style engine, a V8, right? So you got 4 cylinders on the left bank, 4 cylinders on the right bank, and these bank-fired, injected engines, all of the fuel injectors on the left bank would fire, and then on the next rotation of the engine, all the injectors on the right bank would fire. And so on a lot of the cylinders, when the injector fired, the intake valve wasn't open. So where does that fuel sit until that intake valve opens? It sits on the outside of the intake valve. And so the evaporation and the mixing of the air and fuel was not ideal. Still better than throttle body. More popular, more common, and a better system was called sequential fuel injection, SFI. And with sequential fuel injection, the fuel injectors fired one at a time on the intake stroke for their particular cylinder. So as the intake valve was opening and air was rushing in, fuel was injecting right into that moving air. And so it would come in and the air is swirling the way the intake runners are designed, to try to get the air to swirl around and get the fuel evenly distributed throughout the cylinder and not give it an opportunity to puddle in the intake manifold, to condense and all that. So that was better, resulted in better emissions, better performance, better fuel economy. And now we have direct injection, where the fuel is being injected into an area that's much higher temperature. And so there's more complete evaporation of the fuel, and they're able to get away with injecting a lot less fuel. You're wasting a lot less. More of the fuel that's injected actually is involved in the combustion process. So to date, direct injection is the most efficient, system we have so far. So back to the point about only liquid fuel burning, because this is important for why these systems are better, the newer ones. If you could imagine I don't know, take a pan, a saucepan, and put 2 inches of gasoline in it. Now, I'm not asking you to do this. I don't want you to do anything dangerous like this. And then strike a match and throw it on top of that gas. What you would find is the flames would be limited to the surface of the gas. It wouldn't be burning, an inch down into the gasoline. It would only be burning as the vapors rise off the surface, they burn, and that's it. Only the surface is burning. Only the vapors coming off is burning. So liquid fuel doesn't burn, fuel vapor does. So the more we can do to get that fuel vaporized, then the better it'll be. This is why a cold engine doesn't run as well. The fuel doesn't vaporize as well. So we need to throw extra at it, extra fuel, and we're running on the percentage of fuel that actually vaporizes. The rest of it goes right back out the exhaust. And so a cold engine does not do very well in terms of efficiency, and the emissions are high. So we're trying to get engines warmed up as quickly as possible so we're not having to throw all kinds of extra fuel in it. So the ratio that we always talk about that's ideal, and this is a term called stoichiometry, for gasoline is 14.7 to 1. Now, as we go on and continue our discussions, you'll find that that number is not all there is to it. In other words, 14.7 to 1 is a ratio of air to fuel, so 14.7 parts of air to 1 part fuel, whether it be 14.7 pounds of air to 1 pound of fuel, 14.7 tons of air to 1 ton of fuel. That's the ratio, 14.7 to 1. That they say is stoichiometry, or they say is the perfect air-fuel ratio for a gasoline engine. There are problems with that, and the problems are, and we'll discuss them later, that, well, in fact, let me look at this next, yeah, we'll get to it. The problem is that as an engine drives down the road, or vehicle drives down the road, the actual air-fuel mixture requirements change. So if I'm idling at 14.7 to 1. And then the light turns from red to green, and I stomp on the accelerator, right? I smash the loud pedal to the ground. 14.7 to 1 is no longer going to be a sufficiently rich air-fuel ratio to give me the power I need for acceleration. So for acceleration, I need a richer air-fuel mixture. And if you look down here, you know, where's my little annotate? Here we go. So when I talk about rich and lean, you know, not enough air is a rich mixture, too much air is a lean mixture. Let me get rid of that. Okay. So there's more to come about that in the next few slides. So let me go back to the dot point above that. You know, so here where I said, whoops, air is 78% nitrogen, 21% oxygen, and 1% other stuff. So one thing you have to realize when air and fuel go into the cylinder, whatever goes in on the intake stroke comes out on the exhaust stroke. If I'm telling you that combustion is the process by which fuel is oxidized, in other words, combines with oxygen, so that explains what happens to the gasoline, and that explains what happens to the oxygen. What happens to the 78% nitrogen that's you know, in the air that's going into the engine? It does not blend with the fuel. You know, the oxygen does that. So what does it do? So in an ideal world, it passes out the exhaust pipe untouched. You know, it's obviously the oxygen is removed from the air and nitrogen just passes out the exhaust pipe. In real life, it doesn't work exactly like that. So when combustion chamber temperatures are really high, and I don't mean when the engine is hot, I'm talking about the temperature inside the combustion chamber is really high, nitrogen can combine with oxygen. And the resulting chemical compound, they're known as oxides of nitrogen, or NOx. And NOx is considered bad. It's a pollutant. So most engines incorporate some way of keeping those combustion chamber temperatures from getting too high. So for years, the way that was done was something called exhaust gas recirculation. Now here's where we talk about the engine performance curriculum and the fuel and emissions, you know, course curriculum kind of overlapping. I'm talking about exhaust gas recirculation, or EGR valves, and that is obviously an emission control, but I feel, you know, that I need to talk about it, and whoever you have for fuel and emissions probably also will talk about it. So what the EGR valve, the exhaust gas recirculation valve, does, it takes some of the exhaust that's leaving the engine, and it recirculates it back into the intake airstream. What that does is it introduces some exhaust into the cylinder along with the air and fuel that's coming in. So think of it this way. If I have a cylinder that holds, you know, 1/2 or 0.5 liters, without any EGR, we would get 0.5 liters of air and fuel in the engine. That's what would burn. If we put, you know, 0.1 liter of exhaust in, now there's only 0.4 liters of air and fuel coming into the cylinder. What does that do? That reduces the temperature of the combustion process. You know, Does it take away from the power? Yeah, absolutely it does. But what we're interested in with exhaust gas recirculation is putting inert, unburnable exhaust gas into the cylinder, and it has the same effect of making the cylinder smaller because it fills some of it up with useless gas that can't be burned. More recently, with variable valve timing, sometimes instead of having an EGR valve, the computer can control the exhaust cam to leave some exhaust in the cylinder at the end of the exhaust stroke, so it's still in there for the intake stroke. In other words, we don't scavenge all of the exhaust out. Again, does this have an effect on performance? Absolutely has an effect on performance. Absolutely. So this is not going to happen. Exhaust gas recirculation or that kind of control of the valve timing is not going to happen under situations where the engine needs to develop a lot of power. It's going to happen cruising down the highway where you're just a steady cruise. The engine only has to make enough power just to maintain a constant speed. As soon as you stomp on the gas, that exhaust gas recirculation is going to stop for maximum power. So there's really no advantage. People used to disable these EGR valves to get more power. With the way things are controlled by computers now, there's really no advantage to that. What happens is, when the engine needs power, the EGR is shut down. So removing it has no effect. The computer takes care of that for you. So one effect that having EGR and reducing combustion chamber temperatures has, besides controlling NOx, it also helps control detonation. Having that air-fuel mixture explode instead of burn smoothly. So I remember when I was, I don't know, in my 20s maybe, I had a Ford LTD. They didn't call them Crown Vics at the time, but that's what it was. And the EGR valve stopped working. And every time I hit the gas, I had detonation, what they call ping. And it was horrible. I couldn't drive the thing without making terrible rattling sound coming, from the engine cylinders, right? Because the air fuel mixture was exploding, detonating rather than burning smoothly. And as soon as I fixed that EGR valve, the problem went away instantaneously. So that, to me, was such a clear indication of how important that EGR was for controlling combustion temperatures, and not only to control oxides of nitrogen, but to keep it from actually detonating. Now, typically, engines have a NOx sensor. If that detonation starts, then the computer can do other things to reduce that. So let me get back on track with the slides here. So fuel will not burn without oxygen. Where does the oxygen come from? It comes from the air. Air is 21% oxygen. The nitrogen should just pass right on through and out the other side without getting involved in the combustion process. The oxygen in the air should combine with the fuel, and the nitrogen should just go right on through. The ratio of air to fuel is about 14.7 to 1. That's what we go with. That does change under different operating conditions. If we don't have enough air, or the other way to say that is if we have too much fuel, right? Either one of those, same thing. We call that a rich mixture. If we have too much air or not enough fuel, we call that a lean mixture. So if 14.7 to 1 air to fuel is correct, then 16 to 1 would be lean, because it's more air, right? 12 to 1 would be rich. That's less air. So that 14.7 is the air and the 1 is the fuel. If we have a rich mixture, the combustion process will run out of oxygen before all the fuel burns. Remember I said burning is the combustion process is combining air and fuel together, oxidizing the fuel. If we don't have enough air, then we're not going to oxidize all the fuel. There's going to be unburned fuel coming out your tailpipe. If we have too lean of a mixture, the combustion process is going to run out of fuel before all the air is used. What are we going to have coming out the tailpipe? Excess oxygen. You know, if we get too lean or too rich, for that matter, then the combustion process won't happen at all, or won't happen completely, and we'll have misfires. Lean misfires would be more common than rich misfires. So vacuum leak, leaning, excessively leaning out a cylinder or something like that can cause that cylinder to misfire. Let me back up a second. So I talked about direct injection, and what the advantage of direct injection is that the air-fuel mixture or the fuel more completely evaporates because you're spraying it into this hot environment, right? This stratified charge, I think Honda, had their CVCC, and there's been other engines that inject the fuel into a small area, and almost like a pre-combustion chamber that gets lit, and then it spreads out into the main combustion chamber. It's a little bit weird, it allows for leaner air-fuel ratios, but still not as good as direct injection. All right, so hopefully you get that. We need a certain correct ratio of air and fuel for our combustion process to happen right. So here, what I'm telling you is here is going into the cylinder, all right? And notice it's methane I'm using because gasoline is a much more complex hydrocarbon compound. We're using hydrocarbon fuels, meaning they're made of hydrogen and carbon. So methane is CH4. Now what does that mean? It means 1 carbon, right? And 4 hydrogen. I gotta remember how to erase everything here. Yeah, whatever. Just like that. So going into the cylinder, we have CH4, all right? So 1 molecule, right, of fuel, methane, right? And we put in 2 oxygen molecules, right? That's what's going into the cylinder. Coming out is the same thing, right? So we have a carbon, right? Matches this carbon here, right? So check both of those off, right? Check mark, check mark. We have oxygen, right? 1 oxygen molecule, right? Here's 2 of oxygen molecules, right? And 2 H2s. In other words, that's the same as H4. So it all adds up that we have the same number of atoms of carbon, the same number of atoms of oxygen, and the same number of atoms of hydrogen. So, nothing is gained or lost in the process there. Things are just, like I say, the process of combustion is the process of combining the fuel with oxygen. So what comes out in a perfect world, what comes out of the tailpipe would be CO2. That's carbon dioxide. All right. Now that's over the years been labeled what they call a greenhouse gas. But the alternative, if that process doesn't happen completely, instead of carbon dioxide, you wind up with carbon monoxide. And carbon monoxide is a poisonous gas that will kill you. Carbon dioxide, I guess, is making it warmer year after year, right? It's what they call a greenhouse gas. But it is a byproduct of complete and normal combustion. And then if you know what H2O is, of course, that's water. And so, it's telling us that we would get 2 molecules of water and a molecule of CO2 or carbon dioxide if this is what we put in, CH4 and a couple of oxygens. They would be recombined during the combustion process to be carbon dioxide and water vapor. So that sounds pretty harmless, right? Coming out your tailpipe, water vapor and carbon dioxide. But this is ideal, right? This is I'm going to say it's a pipe dream. This doesn't actually happen this way. Invariably what happens is not all of the fuel burns. So you have hydrocarbon emissions. So what are hydrocarbon emissions? Those are unburned fuel that comes out the tailpipe. The other sources on a vehicle of hydrocarbon emissions are, any fuel vapors from the tank. In California, they got really crazy. When you fuel your vehicle, there's like a vacuum system to suck up any of those, right at the pump nozzle to suck up any of those fuel vapors and feed them back into the system. So they don't even want that. And hydrocarbon emissions are the reason we have evaporative emission systems, canisters and, evap monitors and evap systems. So hydrocarbon emissions are bad. And inside a engine combustion chamber, if some fuel remains unburned, you will have hydrocarbon emissions coming out the tailpipe. So those are considered not good. And the more technology has improved and the more they're able to control air-fuel ratios, and when they come up with direct injection, fewer and fewer hydrocarbon emissions make it out of the engine. So then we have another emission control device, which you'll learn about in fuel and emissions, but that's the catalytic converter. And the job of the catalytic converter is to take those unburned hydrocarbons and combine them with oxygen, and in so doing, turning them into CO2 and water vapor, right? So in other words, it's almost like finishing the combustion process that was supposed to happen in the cylinder, but didn't happen 100%. So the catalytic converter kind of finishes the job, takes any unburned hydrocarbons and finishes oxidizing them. So it's called a conventional oxidation catalyst. That's what it does. It oxidizes the unburned hydrocarbons. So where does that oxygen come from? Sometimes there's an air pump that actually blows air into the exhaust system, so there's oxygen available for that. The catalyst, you should note, does not actually get involved in the process. In other words, none of the material of the catalytic converter is changed in the process. What a catalyst is in chemistry, a catalyst is something that causes a chemical reaction between two other chemicals, but doesn't get involved in it itself. So it's kind of like somebody that instigates a fight, and then steps back and watches two people beat each other to death. What are catalysts? Heat is a catalyst. In the chemistry world, they stir two things together and then heat them on a burner, and the heat causes a chemical reaction to occur between the two things in the test tube. So that explains what happens to the fuel, you know, the hydrocarbon emissions. Now let's talk about, remember I said if we have incomplete combustion instead of CO2, we might have instead CO, the dreaded carbon monoxide. You know, we have carbon monoxide detectors in our house because it's very dangerous. If you have a leak in your chimney or something like that, it can be very dangerous if your dryer vent isn't right. So carbon monoxide is bad, and carbon monoxide is just, you know, it's another byproduct of incomplete combustion. If the carbon and the oxygen don't combine cleanly or completely, instead of the carbon, you know, what's the word I'm looking for? Bonding with two oxygen, you know, atoms, it only bonds with one. So typically, if you see high levels of CO, you probably have an over-rich fuel mixture. If you see high levels of unburned hydrocarbons, you may have misfires. They can even be caused by too lean of an air fuel mixture. But if the cylinder doesn't fire correctly, you're going to have a lot of hydrocarbons in the exhaust. This is why a dead misfire on a cylinder causes a flashing check engine light. If you throw too many unburned hydrocarbons at a catalytic converter, it overheats it, and then it melts down. So the bottom of this slide, well, maybe I should finish. All right, so what's missing from here? What's missing is the nitrogen, right? So coming in, what do we have? Let me see if I can write this. I think I can. So coming in, we have hydrogen. I got to change this color. Wait a minute. Black. There we go. Let me get rid of this. Don't want that. We'll do it again. So we have hydrogen. We have carbon. So that's the gasoline. And we have oxygen. Okay. And we have nitrogen. Coming out, you know, we have hydrogen, we have carbon, we have oxygen, and we have, nitrogen. Just recombined into different compounds. So what we want is for the nitrogen just to come out, you know, the same way it went in, not combining with oxygen chemically and forming oxides of nitrogen. All right, well, let me get rid of that now. Okay. So I want to point out here, right, several different fuels. And of course, gasoline is the one that we are, you know, most familiar with for automobiles. But you know, most of our fuel has 10% ethanol, E10. So you go to a gas pump, you look and it will tell you it's 10% ethanol. You can buy ethanol-free fuel. You can buy that usually places that are somewhere near where people have boats, because ethanol mixes with water, so that means your gas is going to mix with water, and that's bad. So, but for automotive use, ethanol is really, really common, 10%. If you have a flex fuel car, it can run on a mixture of gasoline and ethanol up to 85% ethanol. They call that E85. So not all cars run on straight gasoline, and in fact, nowadays, almost none of them actually do. Why? Almost all of our gasoline has at least some ethanol in it. So it's 90% gasoline, 10% ethanol. So in our cars, we are not running straight gasoline. So this 14.7 to 1 air fuel ratio that we call stoichiometry, right? This stoichiometry, that's no longer really applies perfectly because of, part of our fuel is actually ethanol, which for ethanol stoichiometry is 9 to 1. That means a whole lot less air, say only 9 pounds of air for 1 pound of fuel, instead of up here almost 15 pounds of air for each pound of fuel. You need more fuel to make the same thing happen, is the bottom line on that. So there is less energy density, less power in ethanol than there is in gasoline. Let me erase these things again. So if a vehicle runs on natural gas, you can run it leaner, more air. Propane, a little bit leaner. Diesel, very, very similar to gasoline. Hydrogen, 34 parts of air for each part fuel. So you're going to be injecting a lot less fuel in. But what we're dealing with 14.7 to 1 if it were straight gasoline. But because we're mixing in some ethanol, which is only 9 to 1, we probably actually are running at like 14 to 1 or something to have stoichiometry for E10, the fuel that most of us are running in our cars. So let me see if there's anything else I want to talk about with this. I don't think so. Just flip to the next page here. Hang on, let me get rid of this here. Yeah, I think I've said enough about this. Again, I wasn't in lab this past week, Tuesday and Wednesday, because of, I was required to stay home because we had a student, most of you know this already. If you don't already, then you do. We had a student test positive in one of the labs for COVID. And as soon as that happens, anybody in that lab, including the teacher, has to go home for 2 weeks. So we didn't get an opportunity to talk this week. Hopefully, I had a test on Wednesday, and by the time you see this video, probably I'll have the results, and you will have received an email that tells you whether or not we're having lab this coming week. Not sure, but we can discuss this. Since we don't have face-to-face lectures, always looking for you to bring things up in lab if you don't understand them. So, remember I said, I don't know, a long time ago, probably a half hour ago, I lose track of time when I'm doing these, that the air fuel requirements for an engine, they change. So depending on the operating conditions of the engine. So engines operate under different conditions: startup, idle, acceleration, wide open throttle, cruise, deceleration. And they do these things both warm and cold. So for startup on a cold engine, it needs to be extremely rich. Now, why is this? This goes back to what I said a few slides back. What I said a few slides back is that only fuel vapor burns, liquid fuel does not. And on a cold engine, when you inject fuel in, a lot of it doesn't vaporize. On a warm engine, a lot more of it vaporizes than on a cold engine. So kind of across the board, a cold engine, you need to throw more fuel at it for it to run right. This is why gasoline engines have chokes. If you deal with a lawnmower or a weed whacker, chainsaw, something like that, there may be a choke on it that you need to use, a snowblower. In order for it to run well, when you first start it, especially on a cold day, and then as things warm up, you can take that choke off. And what the choke does is it blocks off the airflow and creates a lot of suction that pulls fuel in through the carburetor. On an airplane, they don't have a choke. What we do on it when the engine's cold on an airplane, we have a primer, which is kind of similar to what you'd see on a weed whacker or a snowblower or something, and it just injects extra fuel into the engine before you try to start it. And the hope here is that you put enough fuel in that the percentage of it that vaporizes is enough to start the engine. The rest of it just goes right out the tailpipe, which is kind of inefficient, but that's kind of the nature of the fuel. So if you look, idle, it's relatively rich. Moderate Excel, this is on a cold engine, somewhat rich. Wide open throttle, very, very rich. Cruise, when the engine's warmed up, it's going to be running at stoichiometry, but when it's cold, it's going to have to be kind of rich. And then on decel, it's going to be lean. So let me correct some of what's on here. So this slides, the trouble with slides is they're kind of, they're a little generic. So let me talk about this for a minute. I have on this chart that when we're at cruise, our air-fuel mixture is 14.7 to 1 when the engine's warm. But in real life, depending on the operating conditions, if you're cruising down the highway at a steady speed, it's probably a lot leaner than 14.7 to 1. In fact, I read somewhere that direct inject engines can run at air-fuel ratios as lean as 40 or 50 to 1 under steady cruise. So take that for what it's worth. As far as on decel, you take your foot off the gas, it's quite possible that the injectors shut off completely and absolutely no fuel is injected. You've got your foot off the gas, you're not needing to make any power, you don't need any fuel. So a lot of the things that I tell you, they're a little dependent on the specific engine system. So an old carbureted engine is going to be different than a direct inject. A diesel is going to be different than gas. We mostly talk about gas, spark ignition engines in here. Let me get rid of that. Okay. This slide here, it's a little busy and it's kind of hard to follow, but the most important thing is to understand what the slide is talking about. So it's talking about conversion efficiency of the catalytic converter. In other words, what air-fuel ratio results in the catalytic converter operating near 100% efficiency? So there are three, on this page, there are three emissions, automotive emissions or pollutants that we're concerned with. Oxides of nitrogen, NOx, right? Unburned hydrocarbons, which is gasoline, and then carbon monoxide, which is, gasoline that has not completely combusted. So something to realize is that NOx, all right, which I said was caused by high temperatures in the combustion chamber, right? So combustion chamber temperatures typically are going to be higher with lean air fuel mixtures. and they're going to be lower with rich air fuel mixtures. One danger, I go back to the airplane thing, right? We are able to control the air fuel mixture manually. In other words, there's a mixture control that when we get up to altitude and the air is thinner and we don't need as much fuel, we're able to pull back on that mixture control a little bit and lean the engine out. And my plane doesn't have it, but the fancier ones, you know, they have exhaust gas temperature, EGT gauges on the dash. And so they talk about peak EGT when they're leaning for peak EGT. And so you start leaning out the air fuel mixture and watching the exhaust gas temperature. And as you lean the air fuel mixture out, the exhaust gas temperature goes up. And you'll know that you're really lean when that exhaust gas temperature gets high. And then typically you don't want to leave it there. You know, you richen it up a little so you're close to peak exhaust gas temperature. And so that just, you know, verifies to me that as air fuel mixtures get leaner, combustion chamber temperatures get higher as a rule. And when combustion chamber temperatures get higher, oxides of nitrogen form more readily, right? So result of high combustion chamber temperatures, oxides of nitrogen. Carbon dioxide, like I said, if we run too rich, we get CO, right? So it's more of a problem over here on this side where we're rich, and not so much of a problem over here where we're lean, right? So right here is that 14.7 mark. Anything on this side, these are lean air fuel mixtures. Anything over here, these are rich air fuel mixtures. So I just got to reset. So notice that the conversion efficiency of the catalytic converter over here, right, is bad for hydrocarbons and bad for CO. It's way down under, like, what is this, about 15% maybe here, right? But the conversion efficiency for NOx is right up at 100% when we're here at this, you know, at this, whatever it is, 13, 14, maybe that's 13.5 to 1 air fuel mixture. So rich air fuel mixture, combustion chamber temperatures are low, oxides of nitrogen are easily dealt with. Up here, where we're lean, right, 15 to 1, 16 to 1, we don't have much of a problem with hydrocarbons or carbon monoxide. So I was telling you before that, you know, we talk about 14.7 to 1 being the perfect air fuel mixture, but it's not. Going back, let me get rid of all this nonsense, right? Going back here, you see under wide open throttle, we need to be very rich. On decel, we need to be very lean. On cruise, we might be balanced to lean. Acceleration, a little bit rich. So what does that mean? That means that 14.7 to 1 is, it's not the best mixture for fuel economy, right? We get better fuel economy with a leaner mixture. It's not the best air fuel mixture for power. We get more power with a richer mixture. So what is it really? What is that air fuel mixture of 14.7 to 1? It's a compromise, right? Here, if we go any leaner, our conversion efficiency for oxides of nitrogen goes down very quickly. If we go any richer, we go this way at all, our conversion efficiency for carbon monoxide and hydrocarbons goes down very rapidly. So in this center spot here, we have acceptable, you know, efficiency, right, for all three of these pollutants. So it's a compromise. It's where the catalytic converter works best for all three. This is what's known as a three-way converter. If you see the term, TWC, three-way converter, this is what they're talking about. One that deals with all three of these harmful emissions. All right, let me close that out. We talked about, yeah, I think, you know what? I think we'll leave it right here.